In section 7.4, we are introduced to trigonometric substitutions, which are basically things that are going to help us use just one more tool to take derivatives. We have seen some things like this with our arc sine, arc cosine, arc tangent, but we're going to run across certain functions that we can't use anything else that we have done so far. One of the things that we are going to go back to is something very familiar, Pythagorean identities, which are listed below, as well as just the Pythagorean theorem. And so all of this section is based on those two principles. They do give you kind of a breakdown of setting up these triangles, but honestly, if you can just remember that in the Pythagorean theorem, you have a squared plus b squared equals c squared. And so when you set up a triangle, you know that setting up your sides, legs don't really matter, hypotenuse matters, because in the Pythagorean theorem, if you have two items added together, then to get what you're solving for is that hypotenuse. But if you have two items subtracted, what you are solving for is one of the legs. And so what you'll notice is that anytime there is a subtraction under here, we are talking about one of the legs. And when we have an addition, we're talking about the hypotenuse. Also, when you have a subtraction, the first term listed, squared, represents the hypotenuse, and the second term represents the leg. In both cases, the first term, the hypotenuse, the second term, the leg. And so what they recommend is that when the number or the constant is squared, they recommend that that be listed as your adjacent side. And when the function or the x squared piece is listed first, the recommendation is that you list it as the opposite side. But even if you do that differently, you will back into really kind of the same trig functions because they will reciprocate. You'll end up with a reciprocal of another way to set it up. So the first example they give us is this function: evaluate the integral of dx over x squared square root of 9 minus x squared. And so you can see they have set up their right triangle. You have the adjacent side listed as your root. So then the first term, the square root of 9, is 3. That has to be the hypotenuse. The second term, the square root of x squared, is x. That has to be the other leg. And so based on this angle, they have set up sine and cotangent. Now you will not automatically go straight to sine and cotangent necessarily. So what you're going to want to do is you're going to want to list your trig functions. If you have the sine of this angle, it's going to be opposite over hypotenuse. The cosine of this angle is going to be that radical adjacent side over the hypotenuse. Your tangent is going to be your opposite over your adjacent. And then you will see your other three functions. They've listed the cotangent. The cosecant then is going to be opposite your sine, and the secant will be opposite your cosine. And so once you get all of these set up, what you're looking for is you are looking to replace every single piece here. And so if I need to replace my x, I'm going to look at where I have my x in the numerator position, because then I can just use this trig function to solve for x by multiplying both sides by sine. And so I will have that x is going to be 3 times the sine of theta. And that's what I'm going to use to replace my x. If x is sine, then x squared is sine squared of theta. If I am looking to replace my root here, square root of 9 minus x squared over, in the denominator there, then I'm going to look at the easiest place to use. Definitely not where I have another x, but where I have just a constant so that I can do the same process and multiply across. So I'm going to use the cosine here. If I multiply both sides by 3, then the cosine of theta is going to equal exactly what I need, that root. And so I'm going to replace that root with just the cosine then of theta. The one thing people forget the most is that they do have to replace the dx. And so I always go back to how I set up my x. If my x is sine, I can just take the derivative of this. The derivative of sine is cosine. And so my dx is going to be replaced with 3 cosine of theta. And of course, now I am using that in reference to theta. And now I can just do my antiderivative. I'm going to use trig or just basic cancellation, depending on what happens here, to do this process. And so I am going to, and actually I want to make sure that I put my letters and my numbers in there. That's 3 cosine, and when I squared my sine, that's a 9 there. But I'm going to do basic reducing, so I can reduce that 3, I can reduce that cosine. For this 9 on the bottom, I can pull that out in front. And I have 1 over sine squared. I can rewrite 1 over sine squared using my reciprocal identities. And now I have cosecant squared. Cosecant squared has a really pretty antiderivative. It is the negative cotangent. And so I can do the negative then cotangent of theta plus c. So I have basically taken my antiderivative, but it's almost like U substitution where I have substituted to solve. So the last step here is to go back and plug back in terms of x, not in terms of theta. So I'm going to look over here and I'm going to say cotangent of theta was defined this way in my original setup. So I need to replace the cotangent of theta with what that meant in my original setup. And now I am done. And of course you can convert and put that 9 in the denominator, just have the negative in front to simplify it a little bit, but you're done with your antiderivative at this point. So the next example just has dx over a root, but you'll notice this time this is addition. Because it's addition, that is going to be my hypotenuse. So then the root of the first term is going to be a leg. The root of the second term is going to be a leg. And I basically set up all of my functions and see what helps me the most. And then decide how I'm going to use it. And so in this case, I would say, well, I have sine of theta is going to give me opposite over hypotenuse. That probably doesn't help me. Cosine of theta, again, that doesn't really help me because I still need a dx. So while this looks like it's exactly what I need, the problem with using this is that it's going to be really hard to get an x out of this, and I have to have an x in order to get a dx. And so you'll notice they got the tangent and they got 2x. Well, that's going to be a really easy one. I don't really need x by itself, but I do need the dx by itself. So when I get to tangent, I see something that would make an easy way to get x by itself, which is also an easy way to get the dx, which is what I need. So if I take the derivative here of both sides, I'm going to get the derivative of tangent, which is secant squared. And so I can replace that dx with 1/2 secant squared of theta delta theta. And so because of that, I'm not going to want to use maybe cosine in the derivative piece with my secant. I could, but then I'm just going to have secant cubed, which is going to take another process to do to be able to figure it out, which again, you could do. However, it's going to be easier to do something that naturally fits well with secant, which is tangent, or either another secant that I can just reduce out of and not have a secant cubed. And so very often it's easy just to get the denominator by itself and put it in the denominator position, because you can see when you take secant, which is hypotenuse over adjacent, you get just the denominator, and it's going to be much easier to use another secant with this secant that I already have. And so I'm going to replace the denominator here with just secant of theta. And then I have, again, a very easy reducing. I have 1/2 then just the antiderivative of secant, which is a known antiderivative. So I can say, well, that's going to be the 1/2 natural log of secant plus tangent. And then again, I'm going to go back to my original and replace my secant with what secant was in the original, which is the square root of 4x squared plus 1. And I'm going to replace my tangent with what tangent was, which was 2x. And then I have the plus c. The last thing we look at is definite integration here. And for definite integration, you literally do exactly the same thing. You are going to find your substitutions for all your parts, and at the end, you're just going to go back and plug in your boundaries and do your subtraction. So I will say, once you solve for x, even the same as with u substitution, you can change your boundaries. So you can see they've set up their triangle here. I need to get this completely by itself, so I am likely going to use tangent to do that. And so I can say, well, the tangent is going to be set up opposite over adjacent, and then to get that by itself, just multiply that over. So I can replace the numerator here with square root of 3 tangent of theta. I do need to get the x by itself, and so I'm likely going to use hypotenuse over adjacent, which is going to be my secant. So my secant then will get my x by itself. Again, multiply that over. That will give me my x. And so I can put that in the denominator, the square root of 3, secant of theta. And as always, I do still need to replace my dx, so I need to take the derivative of this. The derivative of my secant is going to be my secant tangent. And I can then replace my dx with all of that. Now for the boundaries, you can leave it as 2 and square root of 3 if you want to, but it's often easier just to go back to what my x was and figure out what those boundaries would be if I plug in my top and bottom. So for example, I have the square root of 3 secant of theta, plug in your top boundary of 2 and solve for secant. Divide by the square root of 3 and do your arc secant to figure out that that is pi over 6. 2 over square root of 3 over 2 would be the cosine there, and so you can figure out that your top boundary would just be pi over 6. You can do the same thing with your bottom boundary. If you plug in a square root of 3, you're going to see that your bottom boundary there is 0. And so then at the end, you don't have to go back and replace it. You can just use your trig function. And so now I can simplify this. I can cancel out my secant. I can cancel out one of those square root of 3's there. And then I can finish solving, pull that square root of 3 out. I'm going to have the tangent squared here. Now, tangent squared doesn't have a pretty antiderivative, so I would use a Pythagorean identity. I would rewrite this as secant squared minus 1, and then I can take the antiderivative of secant squared, which is much prettier. That is tangent. One thing I do want to point out that this would be just the variable, and in this case, my variable is theta. And then I'm just going to do the process of plugging it back in and solving for my definite integration here.